morning. It is a real privilege to have Jim with us this morning to talk about a project that he says he's been working on since 2014. Jim is a hydrologist supervisor from MDH, working in the Source Water Protection Program. And he's been with MDH since 1989, and for much of that time, he says, been responsible for delineating wellhead protection areas and assessing the vulnerability of public water supplies, supply wells and aquifers in Minnesota. He has received his education from the Miami University and the University of Michigan with a bachelor's and master's degree. And he says in his introductory material, he had an early career in mineral exploration and mining. Jim, welcome to our seminar. It's good to have you.
Yeah, thanks, Mark. Yeah, I've been with MDH long enough that I was able to watch the Des Moines lobe recede in the distance and wave goodbye to it. So no, it just feels that way some days. But yeah, thank you for that introduction. So you're right. This project has been grinding along for a number of years. And I think Mark and maybe some of the rest of you that are on this talk this morning were introduced to it at other presentations in the past. And Mark referenced the fact that we gave a special session on this at the Water Resources Conference last fall. And that may have been another opportunity for some of you to get your feet wet in what this project was all about. So if you attended those talks, some of this is going to be old hat for you, but I promised Mark I would spice it up by adding some new material, so there is some new stuff at the end. So even if you've seen past presentations, especially the water resources presentations, there will be something new here for you. So yeah, this project has been grinding along since 2014 when we first got our appropriation to work on it. And at that time, it was called the virus study. So you're going to see reference to, in this talk, chronologically to the virus study and then converting over to the Pathogen Project for this last iteration. And we think it was a wildly successful rebranding effort to go with a name like the Pathogen Project. It sounds like a Dan Brown novel. And if anybody does pick up the film rights, there's a clause in my contract that I have to be played by George Clooney. So I think that's only fitting. So I'm going to give you a synopsis of the past phases of this study, the virus study, and now the current iteration, the Pathogen Project. Okay, so acknowledgements. If I called out everybody on this list, it would take half my presentation. So I'm going to do this short shrift, but just to say that a lot of folks have been involved in this project. I'm going to call out the Clean Water Council, Clean Water Fund that appropriated the money for the project, the Laboratory for Infectious Disease and the Environment, which is a USDA, USGS lab in Marshfield, Wisconsin, Dr. Mark Borkart and his folks. They've done all the qPCR analysis for the microbes, and they've been a great partner. They added some extra analytes that we couldn't have afforded otherwise. The USGS, Upper Midwest Water Science Center, they're our primary partner on this phase of the project, the Pathogen Project, and then the Minnesota DNR, their dye trace team, led by Paul, Jeff, and John. And then lots of folks at MDH to be thanked as well. So the impetus for the study was largely came from headlines coming from our neighbors to the east in Wisconsin, not having to do with the Packers, but in this case having to do with them detecting viruses in groundwater settings, various groundwater settings. And these are a smattering of publications that came from their work. They were finding them in settings where you might expect that, in shallow sand and gravel sandstone aquifers, in Door County where you have shallow karst environments, but they've also were detecting them in deep confined aquifers in the Madison area. So this caught the attention of the Minnesota legislature and us at MDH, and the legislature appropriated money for us to start this initial study in 2014. And this is what that initial phase of the study looked like. It ran from 2014 to 2016, and it was called the virus study at the time. And it consisted of 145 community and non-community wells distributed around the state, as you see in this figure. Most of them were year-round systems, and they were sampled bi-monthly. There were two phases, the 2014 to 2015 and 2015 to 2016. And in 2014 to 2015, there was a batch of wells randomly selected. And then for the second phase, some of those were retained. And then we added some additional wells where we wanted to provide focus in some geologically sensitive settings. So anyway, and all told, we ended up with 145 wells. 117 of them were sampled bi-monthly for 1 year, 28 of them bi-monthly for 2 full years. And the focus was analysis of fecal pathogens and their indicators. So these were the human enteric viruses, the viruses that live in the guts of humans and are passed in our stools. Then there were other indicators like salmonella, which is more of an agricultural contaminant, Bacteroides, human and bovine, and then the protozoa, Giardia and Cryptosporidium. So that's why the name of the study eventually was changed to the Pathogen Project, because we looked at much more than just viruses. There was also a community illness study that went by the acronym of WAVE, and please don't ask me what that stands for, because despite my long association with this project, I've never fully grasped that. But that consisted of weekly sampling for these microbes at 4 sites in the state. And along with that weekly sampling, there was a survey of residents for illness, symptoms of illness, gastrointestinal illness, and then survey questions having to do with water use and consumption. So the idea there was to try to see if we could pin occurrence of pathogens in groundwater with actual disease outbreak. In addition to the kind of fancy microbial analyses done by qPCR method, there were a bunch of more standard analyses conducted. So the other analytes are shown on the left side of this column. At the top were some microbiological ones, the standard ones, total coliform and E. coli, enterococci, and then a bunch of inorganic contaminants, or not contaminants, but indicators that were looked at. I'm not going to read them off, but if you go down to the bottom of the list, we also looked at the water isotopes, tritium, and the stable isotopes of water to get a sense of the age of the water, and then any indication of surface water influence from evaporative signatures. And we took field parameters using YSIs. You can see a picture in the lower right there, one of our field staff calibrating his water quality sonde. So these are just some pictures of the field activities. It was very labor-intensive sampling. The target was to run 800 liters of water through what is basically a dialysis filter. That's what captures the microbes and is sent off for analysis. And so these are some photos of our field staff. You know, they were gloved up, used sanitary methods for connecting to the water supply and throughout the sampling, and then shipping to the lab. Samples were shipped and received within 24 hours to the Marshfield Clinic. And these are some pictures of some of the field sites and collecting field parameters, etc. So the core of this work was to analyze for the occurrence of genetic material from these microbial pathogens. And so what happens is the picture on the lower left is the actual dialysis filter, through which we would run about 800 liters of water. We would ship that off to the lab in Marshfield. They would elute, backflush, extract from those filters a little aquat that would get fed into their magic, I was going to say black box, qPCR machine. From that machine, there would be report out the genome copies of any of the microbes we were looking for. And basically, these are strands of DNA or RNA, remnant genetic material from the the occurrence of these microbes. Okay, I'm gonna, since I am a geologist at heart, I'm gonna spend some time characterizing the geologic setting, the hydrogeology of the of the study wells. And so this image is to show the distribution of the wells compared to the pollution sensitivity of near surface materials as published by the Minnesota DNR. And so the warmer colors on here represent higher geologic sensitivities, shorter times of travel from the land surface into the groundwater system. You can see the wells kind of span a wide range of near surface pollution sensitivities. They span a wide range of geologic and geographic settings. In terms of aquifer type, in that table on the left, you can see that most of the wells were finished in glacial sand, but we captured all the major aquifers: Paleozoic sandstones, Precambrian crystalline rocks, other parts of the Paleozoic system, the limestones, sandstones, and shale units. If you break that down into percentages, most of the wells were finished in glacial sand, but if you compare that with the percentages of all public supply wells, for which we have almost 7,000 in the state, the percentages across by aquifer type are actually relatively comparable. So that wasn't a stated intent of the study to capture a representative cross-section of aquifer types, but it ended up turning out that way more or less. So we feel like it's a relatively representative cross-section. Some more information on the well characteristics. These are all public supply wells, but of various types. So 88 or slightly more than half were community type wells, the ones that serve municipalities and other large resident populations. And the remaining wells were all non-community, and those fall into either non-transient or transient. And the non-transients are more like the factories and schools where you have more of a regular population, larger populations, and then the transients are more like the gas stations, rest stops, restaurants, where you have more of a transient population being served by the water supply. If you look at the pumping rates of the wells, now this isn't the instantaneous pumping rate, it's the average pumping rate based on water use in a given day. Most of these were not exceptionally large pumpers. I mean, most were in the less than 20 gallon per minute range when you break it down that way. There certainly were some large pumpers in the study, but by and large, these are pretty marginal, run-of-the-mill type public supply pumping wells. If you look at the depths of the wells, so this graph and table reflect that. We certainly had some very shallow and some very deep, but by and large, most were kind of middling in terms of depth, most in the 100 to 200 foot depth range, which is, kind of your run-of-the-mill public supply well depth in the state, I would say. So again, we feel like while we captured the edges of the bell curve, the focus was on the middle. So we feel like it's pretty representative that way. If you look at the thickness of the aquifers from the well logs, most of the wells were finished in sand and gravel aquifers that are in the range of 10 to 20 feet in thickness. And the thicker aquifers that you see in this bar graph tend to be the Paleozoic sandstones and limestones. If you take the specific capacity data for the wells and break it down to a hydraulic conductivity range, again, what you see is that most of these wells don't have screaming high hydraulic conductivities. These aren't, I wouldn't say exceptional in that way. Most were 20 feet per day or less in terms of a K value. So again, I wouldn't say these are necessarily screaming high hydraulic conductivity values for these aquifer wells. If we look at the geologic sensitivity, I'm going to spend a moment on this concept. It's probably one most of us are familiar with, but just want to spend a moment with it because it's important. If you look at a graph like this or a picture like this where the wells on the left are finished in sand and gravel with no geologic protection, but increasing depth to water. And as you go to the right, you get increasing depth and increasing amounts of geologic protection over the well screen. You'd expect the geologic sensitivity or the time of travel from the land surface to the well intake to increase going from left to right. And if you color code that, that's what the hotter colors represent, are the higher geologic sensitivities, and then the cooler colors represent the lower conceptually. And then, you know, the DNR and others who've been involved in geologic sensitivity work in the state have gone so far as to put vertical time of travel estimates to these ratings. So for the very high geologic sensitivity shown on the far left here, it's expected that only hours to months would be needed for water to move from the land surface to the well intake, whereas as you move to the far right, where you have a great thickness of clay or other confining material over the aquifer, you might expect centuries or more to be needed to move through that confining unit. So that's kind of a standard working model that has been used for a long time in Minnesota. If you follow that color coding through to this graph, I've broken up the virus study, if you will, wells into the different categories based on percentage, and then compared them with the percent of all Minnesota public water supply wells for which we have information to make that assessment. It's a lower number in this case. But again, it's not a one-for-one match, but I would say that we categorized or included wells from each of the geologic sensitivity categories, you know, more or less representative fashion. And the other thing I wanted to take away from this graph is that the microbes we're looking for are thought to have a subsurface survival time of no more than 1 to 3 years. Most researchers think it's a year or maybe even less. So if these vertical time of travel estimates based on geologic sensitivity are at all accurate, you really shouldn't be seeing these microbes show up in wells that have geologic sensitivity ratings of moderate, low, or very low. They should be restricted to the very high or high categories. And spoiler alert, that's not how it worked out. So here are the study results from 2014 to 2016. 95% of the wells had one or more positive results for one of the microbes we were looking for. So kind of a staggering number. If you look at the next row down, wells positive for more than one microbe, again, 84%. Wells that were positive in more than one sampling round, similar, 81%. Wells that had at least one result above 10 genomic copies per liter, which is a loosely held threshold for high concentration for these types of parameters, 44%. Again, a fairly high number. Wells positive for Cryptosporidium, 40%, which was really kind of staggering because up to this point, it was thought that Cryptosporidium was a more or less exclusively a surface water contaminant. It's a large protozoa, and how it moves through groundwater systems is a little bit of a head scratcher. And then lastly, wells positive for Giardia. That's where you finally get a big drop, only 4% of the wells. But taken on the face of it, those are pretty staggering results. If we break this down into kind of a high-level summary and do it a bad news, good news approach, the bad news is the microbial detections were widespread. 32% of wells had at least one human virus detection. 70% had at least one human pathogen detection. Some were at high concentration above that 10 genomic copies per liter threshold. The traditional indicators, E. coli and total coliform, did not generally correlate, didn't predict pathogen detection. And lastly, the larger diameter pathogens, the protozoa I mentioned, Giardia and Cryptosporidium, especially Cryptosporidium, seem to be entering groundwater in ways that are a little bit baffling. But let's flip to the good news. The detections were very intermittent. If you look on a per sample basis, not a per well basis, only 6% of samples had a human virus detection and only 22% had a human pathogen detection. The concentrations were usually low, usually below that 10 threshold that I mentioned. And then it's important to realize that not all detections represent an infectious organism. We're looking for strands of genetic material that may or may not be part of an intact, viable microorganism that can infect a person. So these detections, while concerning, may not necessarily have a health risk outcome. And then lastly, not all infectious organisms result in illness, even if they are intact and infectious. So it might be cold comfort, but there is good news coming out of that also. So, I characterized the study wells in a way that explained, I think, that they weren't exceptional in terms of being risky construction. They weren't all in sensitive geologic settings. They weren't all super high capacity use. And those types of indicators, if you will, have generally been good predictors for us in terms of assessing wells for risk from chemical contaminants, for example, nitrate, excuse me, nitrate, petroleum compounds, things like that. But it seems like that breaks down a little bit when we're looking for these genetic components of microbial material. So despite the fact that these wells weren't exceptional in the ways I just described, many of them yielded detections of genetic material. And what I think that means is the abundance of occurrence must mean that this genetic material is fairly widespread in the subsurface. And that also to me means that there's probably multiple transport pathways rather than a single one that we can put our finger on. So what do you need for a microbial contamination to occur? Well, you need a pathogen source. That could be, a sewage, could be sanitary sewer or an ISTS. It could be land use application of manure or biosolids. And then you could have, you need a transport pathway. You need to have some type of pathway, either via well construction, by the native geology or the surface conditions, ponding water, for example. And you seem to need a special event, a recharge event, pumping, inducing vertical gradients. And then there has to be illness circulating in the community, it seems, to keep this cycle alive. So our current conceptual model about how this is happening is based on publication by Hunt et al. 2010, and it's a concept of low yield, fast flow pathways. In other words, small volumes of water moving relatively quickly, being driven by recharge events and exploiting fast flow pathways in the subsurface. And we think those can include fractures in aquifers or confining units. It can include well construction shortcomings, annular spaces being open, casing flaws, gaps in confining units, and unsealed abandoned wells, for example. So I just wanted to touch briefly on the key findings from the WAVE study. So they did find higher rates of acute gastrointestinal illness during weeks where viruses were detected in the drinking water source. However, those didn't hold up to statistical significance, so we can't draw firm conclusions as we would like. It raises questions whether the outcome is due to chance or if the association is real and just that the study was too small. There wasn't enough statistical power associated with it. Another outcome was that we found that people who had a water filter at home had reported higher rates of illness. So that to us tells us that, if you're not maintaining those, they can actually be breeding grounds and be more of a problem than a fix for people. All right, so if we pivot to the current phase of the project, which is the Pathogen Project, as I mentioned, it focuses on these three components that I show on the left side of this table. So there's a statistical analysis piece that's ongoing, and the goals there are to do a better job of addressing our ability to predict pathogen occurrence. We want to look at what the causal factors might be related to these occurrences and see if we can come up with better models for prioritizing public wells in terms of pathogen risk. And then the last two project components are tied together. So we picked 4 from the 145 wells in the previous phase of the study to do very detailed work on recharge event monitoring and tracer studies. And I indicated there that USGS is our primary partner on the recharge event monitoring and the DNR on the tracer studies. The recharge event monitoring is to try to get a better handle on the timing and duration of microbial threats from these recharge events. As I'll note in a minute, it seems like they're related to these precipitation events, so we want to get a better handle on that. And the result might be that we can maybe give guidance to public water systems on how they can better ride out these events, either through using storage or increased treatment. And then the tracer studies are to try to help document the pathways by which this pathogen, by these pathogens travel to the into the subsurface. You know, are they coming from specific parts of the wastewater system? And if so, what are the times of travel, the actual times of travel from the wastewater system to the well intake? And we're hoping that the results from that phase of the study can be used to provide enhanced information on well construction for public wells or setback distances, perhaps in some settings. To talk about the statistics for a bit, the factors being evaluated as possible controlling variables include well construction and use, some of the things I talked about earlier in the talk. The characteristics of the aquifers and their confining units, the chemical and isotopic indicators of human impact, so the tritium, the chloride bromide ratios, things like that. Precipitation amounts and timing, that's the that other concept that I mentioned about recharge events. And then land uses and potential contaminant sources within the capture areas for these wells. What I mean by that is for each well in the study, we generated a 1 and 10-year capture zone via groundwater flow models. And we've inventoried potential contaminant sources within those areas and characterized the land uses based on available statewide data sets. And then for each public well, we do an inventory of potential contaminant sources within 200 feet of the well. That's called the inner well management zone. So we're also comparing what we found from that information with occurrence. We're looking for evidence of surface water interaction via water isotopes and the flow modeling outcomes. And then we're using LiDAR to generate runoff catchment areas, if you will, for each well in the event they happen to sit in a low spot and might be receiving surface water via runoff. This is a sneak peek into how some of that univariate statistical analysis is shaking out. So these are some of the well characteristics that seem to have some bearing or association with microbial outcomes. And most of these you won't be too surprised at, probably depth cased. Both well depth, total well depth, and depth cased showed up, but depth cased we think is a firmer indicator of potential microbial risk. Well casing diameter and discharge rate, those are directly linked. Larger diameter wells generally pump more. So we're going to pick one of those to move into the next phase of modeling. But suffice to say that there does seem to be an impact with larger diameter and higher pumping wells. The drilling method, it seems like the wells that don't create much annular space maybe have slightly less risk associated with them. So cable tool methods, for example. Related to that, grouting, the presence of grout and the amount of grout that's water saturated seem to be factors that maybe play into this. The year drilled or age of the well, again, that makes some sense. As wells age, they're more likely to corrode and develop shortcomings. Depth to bedrock, for wells finished in bedrock, that seems to be a factor. The aquifer type, whether there's any indication of karst or fractured conditions. Geologic sensitivity, although not the silver bullet that it seems to be perhaps for some of the other chemical indicators that we use it for, it does seem to have some play here. Vertical hydraulic gradients, we tried to assess that to see whether gradients were up or down in the proximity of the public well. That was included in the study, and that does seem to be a factor that's shaking out. And then lastly, groundwater age from tritium. Tritium, as you know, is used to assess age residence time of water in the subsurface, and its power has diminished with age because the strength of the atmospheric signal has decreased over time since atmospheric testing of nuclear weapons ceased. But it still seems to hold some promise. But I will tell you that even wells that had no detectable tritium still showed occurrences of some of the microbes in this study. The preliminary shakeout of precipitation analysis is that the greatest total microbial loads were observed within 2 and 7 day lag periods after a heavy rainfall. So that's a useful insight. And then in terms of human enteric virus occurrence, it seemed like there was most closely associated within 24 hours of a precipitation event. So what seems to be, what this is telling us is that these precipitation events seem to trigger these microbial flushes, and we've used this information to help tailor this final phase of the study. And the final phase of the study I want to talk about first is the recharge event monitoring, and this is what we've used that precipitation statistical analysis to help inform. So this work was pioneered by USGS in Wisconsin again, and Dave Owens is the primary author on this article in Groundwater from 2018. And he's really the MacGyver of the USGS, as far as I can tell. He builds these auto samplers from scratch. He gets a beverage cooler and then modifies them with the ability to put 8 of these dialysis filters in sequence in there, and then he attaches modems and water quality sondes. And so water, and then there's a weather station associated with this, and then an adjacent ob well, which is recording water level in real time. So all this information can be tracked in real time, and the sampling can be triggered via cell phone. So as I'll describe, what we do with this phase of the study is we picked 4 wells that we've equipped in this way, and the pictures on the right show this beverage cooler setup with the filters and the modem on the top. And here's one actual installation in the upper right from one of our study sites. And we're watching the weather and triggering sampling to coincide with precipitation events. And this is kind of the generalized view of how that is supposed to go. So we look at the weather 10-day forecast, and if we see a significant rainfall event, so I'm talking about anything in excess of about ½ an inch, we start a background phase of monitoring. That's what this first dot is on this graph. And then a few days later, we'll do another background sample. And then the day before the precipitation is supposed to hit, we'll take another background sample. And then we'll go into daily monitoring for a week after that. And then we'll go into a post phase where we'll start to diminish frequency of sample collection. And the last sample is collected 3 weeks after the start of the first one. And so that's, I've represented this in terms of this kind of arrow at the bottom that shows low intensity sampling in blue, and then red ramping up the frequency. And so that's how it's supposed to work at each of these sites. These are the 4 sites. We could only afford to do this at 4, so would have loved to do it at more. The other thing to keep in mind is that these 4 systems have been working with us for almost 8 years now on this project, and that's an incredible amount of patience to put up with the meddling that we've done. So we could only ask that of so many public water suppliers. But we have a site up around Ely. We have 2 in central Minnesota, and then we have 1 in the metro area. The one up by Ely is a well finished in fractured crystalline rock, Precambrian rock. The 2 in central Minnesota, one's a water table sand, and the other one is a buried sand. And then the one in the metro area is in the Paleozoics in the Wanawak sandstone. As I mentioned, we rely heavily on forecasting tools. It doesn't always work, but we've had pretty good luck. We get daily emails from NOAA that give detailed looks at a variety of things. I've shown the study sites now in red stars on here just to give you a sense of placement. The graphs at the bottom show the state weather forecast on a daily basis with the colors indicating anticipated rainfall intensity, and the greens and deeper blues represent higher intensities. The graph at the top, or the map at the top of the state, shows winter conditions. So yellow represents snow on frozen ground, blue represents frozen ground. And if it's not one of those colors, then the ground has thawed. And we use this to trigger this information to trigger sample collection with the loss of snowpack and thawing of the ground this spring. And there's a good example of that if you trace the day after day forecast up in the Ely area. You can see they started off with snow on frozen ground, and then as the days went by, they lost all their snow and the ground thawed, and that's when we triggered sample collection. This is what sample collection looks like. It's taken that concept that I explained a moment ago with the, we run this out for 3 weeks, starting with the background phase, and then go to a high intensity phase and then a post phase. Well, that's what this looks like for that Ely site this spring that coincided with the loss of their snow cover. I mentioned the fact that there's a paired non-pumped well nearby, a couple 100 feet away, that's used. It's got a data logger in it, and we get the hydrograph from that in real time. That's what the black line is in this graph. You can see that the water level was going down, down, down. They lost their, started losing snowpack, started losing frozen ground, and the hydrograph started coming up, up, up. And the arrows here represent our sample collections. So we caught the bottom of the hydrograph, and then we caught it coming up this rising limb up to the peak here. And so we feel like we got a pretty good capture of the rise on that hydrograph. The green line on here represents accumulated precipitation. So over the same time period, they lost snowpack and they had a couple inches of rainfall. So we thought that was a pretty successful event. At the same time that the water filters are filling, and that's what's represented in this graph from that Ely site, when these yellow lines kick off and come up into this range, that means the filter is filling, and then it goes back into non-filling phase and it fills again. Everything else on here represent water quality parameters coming from a sonde that's through which the water is flowing on in a separate branch from the water flowing to the filters. And we're capturing real-time all the standard field parameters, plus some extra ones like tryptophan, which comes in handy around Thanksgiving. Just kidding, it turns out that that's a really good indicator of wastewater influence. Optical brighteners, and then at a couple of sites we also have, and here we have chloride and bromide sensors, and a couple of sites we have sensors for rhodamine and eosine, fluorescein dye, where we have dye traces going on simultaneously. Okay, so let's, I think I promised Mark a sneak peek at some results, and we have very few so far from this phase of the recharge study, but we do have some from the start of it last fall. Our first sampling took place last September, October, and what I'm showing here is a graph. The top part is accumulated precipitation during a fall recharge event that occurred up in the Crow Wing County area around September 10th or 11th. And you can see that over the following couple of weeks, I guess, they received up to 3 inches of rainfall. And here's the associated hydrograph at the nearby Ob well. It was dropping through the fall, and then it stabilized with the start of this recharge event. A little bit of noise, not as high or discrete a rise as we saw at the Ely site, but still you could tell that it was a change in the hydrograph. And those bars there represent our sampling results. We triggered sampling during this first event in late September, early October, and then we did it again in November when there was another recharge event. So following those sampling duration and frequency bars forward, these are some results. This is total microbial sum and genomic copies per liter for all the microbes we were looking at. And again, the blue on here represents the post event monitoring phase, and the pre and post monitoring event phases, and then the red is the high intensity phase. And in this case, we didn't get all the background samples we wanted because we got surprised by the forecast. But we did have one background sample that was non-detect, and then we went into high intensity phase, and sure enough, there was a spike in microbial sum. It did drop back down and then flash back up about a week after the first sample collection. So it seemed like there was maybe a first pulse and then a second pulse, and then it finally settled down. So it's that type of information we're hoping to use to help guide our conclusions and recommendations to public water suppliers. And associated with these sites, we've done tracer studies. This shows the DNR team using brine and fluorescent dyes. The dyes were being used in wastewater components of ISTSs, and then we monitor for the occurrence of the dyes at the well. And then there was salt used at a stormwater intake. We were looking for a rise in the conductance value at one of those sites. So the ideal outcome here would be to come up with some standard information on precipitation, contaminant sources, geology, general water quality, to be able to better predict pathogen detection and improve health risk outcomes. I'm going to wrap up by talking about what some of the potential fixes are from some of the work that's been done so far and might continue to shake out of this. So, some of our investigations have showed that, yeah, there were some fairly egregious things that could be fixed. This is a sanitary sewer line coming from a facility going out to their ISTS, and there was like a 2-inch gap between one part of the pipe and the next part. So there was, basically raw sewage entering the ground there a couple hundred feet from the well. Other fixes include siting replacement wells. This is a case where the red here shows the well capture area for one of the study wells. You can see that there are septic systems and drain fields within that 1 year time of travel capture area. The facility said, what can we do to get a better well? And we said maybe siting that well outside of the zone of influence of those septic systems and drain fields. And they did put in a new well in that area and have had better outcomes. Other fixes might be utilizing storage during recharge events. As I mentioned, if we can fine tune when these microbial pulses occur, how soon after recharge events, we can maybe give guidance to public water suppliers on how they can, fill the tank a few days before a recharge event. Depending on water use in the system, they may be able to ride it out if it's 24 to 48 hours is the main flush. And then, better management of land uses and increasing isolation distances between wells and possible contaminant sources might be another outcome from this study. Improving well construction and sealing, it may be that we come up with, from the statistical analysis, come up with some recommendations based on, what the best construction methods might be to best avoid some of these microbial situations. And then the last line of defense in our view would be adding treatment, and that's always an option, but we'd rather hold that as the last defense. The figure on the right shows a UV system that was installed at one of the sites where we had some concerning results from the study. And that's what I have. I wanted to leave a few minutes for questions, and I think I've done that. Yeah, got about 10 minutes, I guess. So I haven't checked the chat. If somebody's monitoring that, you want to forward anything on, I'd be glad to take it.
Yeah, well, thank you for
Sounds good.
your talk. Right now, I have not seen any comments in the chat, but okay, here we go. So start putting your comments or your questions in the chat, everyone. So our first question is, how did COVID impact your study?
Yeah, good question. It caused a delay in the start of this final phase of the project with our recharge monitoring and the tracer studies. We had to put that on hold. We had planned to start that in spring of 2020. Instead, we had to push it back to fall when restrictions were lifted for us to carry on that part of the study. So we had to amend our agreements with the USGS and the DNR, push all the timing back. And then we also added the SARS-CoV virus to the analytical list, just in case we saw evidence of it floating through the subsurface and being captured at these wells. So we modified our parameter list also.
Great, thanks. We have another question. Was the UV added to a water treatment plant?
It was added to a transient public water supply system. So they didn't have a treatment plant per se. They just had water coming in to a pressure tank and then distributed to the facility. So it was added to that flow so that the water being distributed to their consumers is now UV treated.
All right, it looks like we've got another question. Are these levels of pathogen virus detection actually pathogenic? Is there any evidence that these levels of pathogens could cause illnesses? As a layman, seems like these levels are very low and potentially below illness-causing levels.
Yeah, that's one of the, it's a little bit of a gray area. What we are detecting are genetic components, but there have been studies that suggest that even though that's what we're detecting, that they can result in illness. Some of the studies done in Wisconsin have nailed that down pretty well. And our WAVE study suggested that, although it didn't, like I said, it didn't rise to the level of statistical significance. Also, while the concentrations, if you will, are relatively low, that 10 genomic copy per liter threshold has been found to be a threshold above which you can often culture these organisms. So if they're culturable, they can be infectious. So while 10 genomic copies per liter, to the layman, or when I first thought about that, it didn't seem high to me either, but it does seem to be high enough that it can be infectious. So we don't want to dismiss these as being a non-issue. By the same token, we have to be careful with our messaging, and we can't say 100% of the time that because we detect a genetic material that it's potentially going to be illness causing.
Great, thank you for the answer. Did the 5% of wells that didn't have a detect have anything in common?
Wow, that's surprisingly, I haven't looked at it from that perspective. I think the answer is going to be no, given the outcome of the statistical work that's been done to date. What's struck me so far from that analysis is that it's giving us some insights, but none of them are super strong, and they're more like subtle. So that question is going to make me want to go back and look at that in more detail. But my off the cuff would be that no, there seemed to be more randomness associated with the occurrence than I would have expected, and I think that means that those that didn't have occurrence are also going to seem relatively random.
Yeah, Jim, this is a great talk. This is absolutely stunning to me, to be honest with you. I mean, the second time that I've seen your presentation, it is as stunning to me this time as it is the first, that you're detecting this level of genetic material from pathogens in groundwater. And with a background in microbiology, it just seems to me that either we have to refine our paradigm of microbial transport in the subsurface, or our understanding of of the subsurface geology and transmissivity to accommodate these results. I mean, it's just amazing to me. Any thoughts about, what you're seeing in a broader context like that?
Yeah, well, I've had the exact same reaction, Mark. There's nothing in my training or education that brought me to the point where I could easily wrap my head around these results. So I'm trying to shift my paradigm, if you will, about how this can happen. And I think, as I mentioned, I think what Randy Hunt and his team published in 2010 is probably conceptually makes the most sense to me, that there must be these fast transport pathways moving small volumes of water that relatively quickly into the subsurface that must be responsible. I think our job going forward as hydrogeologists is to try to nail down what those might be to the extent we can. And I feel like maybe the best thing we can do at this point is to focus on some of the things we're trying to answer in this phase of the study. If we can, even if we can't identify specific pathways, if we can identify the timing better related to certain amounts of precipitation, we can at least provide guidance on how to better ride out these events, how to use treatment, how to use storage for public water suppliers. But I think maybe the next generation of hydrogeologists are really going to have to take on this mantle of trying to figure out what these pathways consist of.
And we do have a few more questions and comments in the chat. One that I want to for sure point out is that George Clooney would be lucky to play your part. So that's one of the comments we've got there for you. Any advice for private well owners?
That's a tough one because these types of analyses are not going to be available to the typical private well owner. I think the best thing that you can do is to continue to have your well sampled on an annual basis for, even though I said total coliform and E. coli were not closely linked to these other microbes, they are still useful indicators for what they are, for those specific constituents. And E. coli can be nasty, nastier than many of the things that we noted here. So you don't want to throw up your hands and say I can't do anything because I can't analyze for these microbes by PCR. I would continue to analyze annually for total coliform and E. coli, nitrate, and arsenic if that's an issue for you. And to the extent that you can manage your, make sure your well is maintained properly, make sure if you have a filter or a filter system, make sure it's maintained and working properly. That did pop up as a risk factor for folks. So yeah, I think there are things public or private well owners can do outside of the context of the fancy analyses.
All right, thank you. We have a few more coming in here. I think you answered one of them in that first, in that private well owner. The other one in here is, was the site with the septic system impacted well cross-referenced with the recommended minimum setback distance from soil systems to wells to see if the current distance is protective?
Yeah, that well did meet setbacks. So, I mean, that is one insight, is that while setbacks are useful for what they are, they probably aren't a silver bullet in 100% of the cases. And, if we gain some insights from the statistical analysis piece or other components of this project, we'll forward those on for consideration to well management and others who might have a say in enhancing setback distances to certain potential contaminant sources. But it's too early to say whether we're in a position to do that or what those increased distances might look like.
Great, thank you. Another question is, has this effort gotten any publicity? Seems like it could attract major media attention and concern.
Yeah, we've had press releases, and there have been 2 publications in journals so far, with more on the way. So, yeah, it's not been hidden by stretch of the imagination. And, you know, presentations like at the Water Resources Conference, that was a full special session. So we've not shirked from publicizing it. I don't actually know how much press attention it's gotten. I think there might have been some with our first press releases, but that's going back a few years now. And it could be that's just it's old news at this point in some sense.
All right, a couple more comments and questions here. It says the small volume piece is important. It makes sense since we don't usually see nitrate or oxygen in these deeper confined settings. Tracing these pathways could be challenging, but knowing they exist is important. Good work.
Yeah, thanks.
And then
I just
ahead.
wanted to do one quick follow-up on that. So another insight into that is, you know, many of the wells that had detectable microbes had no detectable tritium, or at least some of them. And that means that, you know, given current tritium levels in the atmosphere, a non-detect can mask about 10 to 15% young water. And we think it's in that 10 to 15% piece that the pathogens are probably also traveling. So it is a small volume, fast transit.
And then can you elaborate on greater illness associated with homes with water filters?
I cannot, because that part of the study was done by our epidemiologists, and I only talk their language a little bit. So I would have to defer you to other team members for a better answer on that.
Okay, so Carol, if you wanted to follow up with Jim, he can get you the contact. And then we just have one last comment here that for those interested, the pathogen data is published in the ES&T and water research, and there it looks like a link has been posted in the chat for anyone who wants to check that publication out.
Yeah, thank you to Tucker and Aaron for doing that.
So I think that does it for questions in the chat.
All right.
So
Jim, thanks
you.
so much for the presentation. It was great.
Oh, you're welcome. It was my pleasure.
And then I will just put a plug here. I'm going to actually post the link to our water issues page where you can find past recordings. And we are almost up to date. So everything is posted up until today's talk. So if you want to just grab that link right from the chat now, maybe we'll start doing that at these meetings to make sure you guys have access to those. So I will get Jim's presentation hopefully posted in the next 2 weeks. And again, it was just really great to have you with us today for sharing your important work. And it's always a pleasure to learn from our colleagues of the great work that's going on. So thanks for your time
absolutely.
today.
Yeah, thanks.
Really interesting work. Just
Thank
as a footnote to that, Jim, many years ago, I was working